In 1999, a research ship collecting sediment cores off the coast of Oregon drifted off course. It was a navigational error, not dramatic, not intentional, just the kind of ordinary mistake that happens on long research voyages in open ocean. The ship ended up approximately 55 miles south of Cape Mendocino, California, in waters that sat above a completely different fault system than the one the scientists were studying. They were there to sample Cascadia. They had accidentally parked above the San Andreas. They drilled anyway. And what came up from the seafloor in that core changed how seismologists understand the most dangerous 1,400 kilometers of coastline on the planet. The sediment was upside down. In normal geology, turbidites, the layers of material deposited on the ocean floor by underwater landslides triggered by earthquakes, follow a predictable pattern. Coarse sand settles first because it is heavy. Fine silt settles on top because it is light. Bottom to top. Coarse, then fine. That is the universal pattern. It has been consistent in every turbidite layer sampled from the ocean floor in 70 years of marine geology research. The core from 55 miles south of Cape Mendocino showed fine silt on the bottom and coarse sand on top. The pattern was exactly reversed. An Oregon State University marine geologist, Chris Goldfinger, when he analyzed what that reversal meant, arrived at the only explanation that fit the physics. Two separate earthquakes had occurred in rapid succession. The fine layer on the bottom was deposited by a massive Cascadia rupture. Before that sediment could fully settle, a second earthquake struck, this one on the San Andreas, directly below the collection site, and sent a new cascade of coarser material washing over the still settling Cascadia layer. Two earthquakes, two layers, stacked so close together that the first had not finished settling when the second arrived. Chris Goldfinger has spent 25 years studying this question. His team drilled sediment cores representing 3,100 years of geological history from the ocean floor along the west coast, focusing specifically on turbidite layers at sites influenced by both the Cascadia Subduction zone and the San Andreas Fault. What they found, published in the journal Geosphere and covered by National Geographic, Scientific American, and Science Daily, is the most significant finding in West Coast seismic research in decades. At least 10 times in the past 3,100 years, Cascadia and the San Andreas have ruptured together or within hours, days, or decades of each other. 10 times in 3,100 years, an average of once every 310 years. And the most recent confirmed paired event was the major Cascadia rupture of January 26, 1700, 326 years ago. The same event that sent a tsunami to Japan overnight. The same fault that scientists confirmed this year is now tearing apart beneath Vancouver Island, sitting at its highest coupled stress state in centuries, showing anomalous slow slip behavior on its central segment. To understand what the paired turbidite evidence actually means, you need to understand what triggers an underwater landslide. The ocean floor off the Pacific Northwest is not a flat, static surface. It is a sloped terrain of sediment, material that has been accumulating for thousands of years, carried offshore by rivers and piling up on the continental slope. That accumulated sediment is held in place by friction and gravity. A large earthquake disrupts that equilibrium instantly. The shaking liquefies the slope sediment and sends it cascading down the continental margin in a turbidity current, a dense, fast-moving underwater avalanche that deposits a characteristic layer on the deep ocean floor, a turbidite. Scientists use these layers as a geological clock, dating when large earthquakes occurred by dating the turbidites they produced. The paired turbidites, the upside-down layers, are the record of something that standard earthquake hazard models did not account for. They are the record of Cascadia shaking so violently, so suddenly, that the surface waves it generated crossed the Cape Mendocino triple junction, the point where the Cascadia Subduction zone, the San Andreas Fault, and the Mendocino fracture zone all meet, and loaded enough additional stress onto the northern San Andreas to push it past its failure threshold. Minutes to hours later, the San Andreas ruptured. The turbidite sequence recorded both events, one on top of the other, in sediment that has been sitting undisturbed on the Pacific Ocean floor for centuries. Stop for a moment and consider what that sequence means for the present day. Cascadia last fully ruptured in January 1700. The San Andreas last fully ruptured in 1906 in the earthquake that destroyed San Francisco. Both faults are now loaded. Cascadia with 326 years of accumulated strain at 4 centimeters per year. The San Andreas and San Jacinto combined at their highest stress levels in 1,000 years, according to the Burkhardt study published in June 2026. If the turbidite evidence describes a real physical relationship, and Goldfinger argues that 10 confirmed paired events over 3,100 years is not coincidence, then the next full Cascadia rupture does not arrive alone. It arrives as the first half of a 1-2 sequence, with the San Andreas following somewhere between minutes and decades later. Chris Goldfinger said something at the Oregon State press conference that deserves to be heard in full. We are used to hearing about Cascadia, the big one, being this catastrophic, huge thing. It turns out it is not the worst-case scenario. The worst-case scenario is both faults going together. He was not being dramatic. He was describing what the sediment record shows. A Cascadia earthquake alone, magnitude 9 or greater, shaking from Northern California to British Columbia for 4 to 5 minutes, generating a tsunami that reaches coastal communities within 15 to 20 minutes, already exceeds the response capacity of every Pacific Northwest emergency management system combined. FEMA estimates 13,000 deaths, 1 million displaced, recovery measured in years. That is the single fault scenario. That is, in Goldfinger's words, not the worst case. The worst case is both at once, or close enough to once that the emergency response to Cascadia is still being organized when the San Andreas moves. San Francisco, Portland, Seattle, and Vancouver in simultaneous or near simultaneous states of catastrophic structural damage and active tsunami inundation. Federal and state resources, the search and rescue teams, the National Guard units, the emergency medical assets, the supply chain logistics, drawn into the Cascadia response zone in the Pacific Northwest and unavailable or severely limited for the San Andreas response zone in California. Goldfinger's own words, "We could expect that an earthquake on one of the faults alone would draw down the resources of the whole country. If they both go, you have potentially San Francisco, Portland, Seattle, and Vancouver all in an emergency situation in a compressed time frame." The study does not claim this chain reaction is imminent. The turbidite evidence establishes that it has happened before, not that it will happen on any particular schedule. Some of the paired events in the sediment record are separated by decades, not hours. The synchronization is probabilistic, not mechanical.
Goldfinger himself acknowledges the uncertainties in radiocarbon dating at the resolution required to determine whether paired events occurred within hours or within years of each other. The practical implication is more familiar than the scientific detail. Both fault systems are loaded, both are historically capable of producing paired ruptures, and the current stress state of both, Cascadia at 326 years of accumulation, San Andreas at its millennium high, places this moment squarely within the geological window in which past paired events have occurred. There is one more piece this sediment record cannot tell us, but the seismological record of 2026 can. The Kamchatka M8.8 sent surface waves through Cascadia. Mexico's M7.3 sent waves up toward the Guerrero Gap and through the southern San Andreas. Venezuela's M7.5 doublet loaded energy into the California fault network 3 weeks ago. Clear Lake Volcanic Field produced 262 earthquakes in a week. Every data point in 2026 describes fault systems at or near their historical stress maximums, receiving external energy pulses from a planet that has been more seismically active in the past 12 months than at any comparable period in recent history. The turbidite core from 55 miles south of Cape Mendocino is 25 years old. The analysis of what it means has been published, reviewed, debated, and confirmed across multiple research teams. The fault chain it describes, Cascadia triggering San Andreas, one after the other, their combined destruction exceeding anything either could produce alone, is not a hypothetical. It is a geological pattern that has repeated 10 times in the past 3,100 years. It is a pattern that the current stress state of both fault systems is consistent with initiating. And it is a pattern that emergency planners in San Francisco, Portland, Seattle, and Vancouver have not yet fully incorporated into the response frameworks that would need to activate simultaneously if Goldfinger is right about what the upside-down sediment is telling us. The research ship drifted off course in 1999. It found something that changed the question from when does the big one hit to which big one hits first. The second question has a much worse answer. Subscribe to Seismic Alert. We will be watching both faults.